This lecture is all about estimating ADL P, Q models. So a quick reminder of the ADL P, Q model. If yt depends on an exogenous variable xt, we can do beta 1 plus beta 2 xt plus an error term epsilon t. Then we call this model a static model. I don't have any lag dependent variables and I don't have any lagged explanatory variables. We can also call this an ADL 0, 0 because we have none of the lagged variables. If I add one lag on the explanatory variable, I can write the model like this: theta xt minus 1 plus epsilon t. So now I have a lagged explanatory variable, and then we call the model ADL 0, 1. If I add a third variable, theta 2 xt minus 2, it becomes an ADL 0, 2, and so on. Also, if I add the lagged dependent variable, like rho yt minus 1 plus epsilon t, then it's an ADL 1, 0. I have one lag on the dependent variable. And similarly, if I add yt minus 2 as an explanatory variable, it's an ADL 2, 0. And of course, I can combine these and have a lag on the x variable and a lag on the y variable. So let's begin by looking at the ADL 0, q. That's a model where I have no lagged dependent variables. Now, remember from the AR1 lecture, as soon as I have a lag dependent variable, I cannot make the exogeneity assumption. So in such a case, the Gauss-Markov assumption, as we have stated them here, cannot be satisfied. However, if I have only lagged on the x variable, then it is actually possible to make the Gauss-Markov assumption. As long as all the x variables are exogenous, then you can make that assumption, and the result will then be what we know from considering a model with the Gauss-Markov assumptions, namely the OLS estimator will be unbiased, consistent, efficient, and have all the nicest properties that we can think of. As soon as I add a lag dependent variable, things get more complex, and we need to look at the AR1 and the ARP process for hints on what to do. For example, if I have the ADL 1, 0, which is basically an AR1 process like this, but with an additional explanatory variable. Well, this extra explanatory variable, which is exogenous, will not change the results that we have developed for the AR1 process. For example, for the ADL 1, 0 process, it satisfies the stability conditions if rho is between -1 and 1. And just like the AR1 process, that stability condition will be a necessary condition for this process to be stationary. We also said that the higher order ARP processes, they do have stability conditions, but they are more complex to express, and those stability conditions will be exactly the same when we look at the ADL P, Q model. So all the stability conditions from ARP with a given P carry over to ADL model with the same value of P but with Q lags of the explanatory variable X. And they will still be necessary conditions for stability. Sorry about the typo. The stability conditions are of course necessary conditions for, well, not stability, but for stationarity. Like this. We also know that if I have an AR1 process or an ARP process, exogeneity cannot hold the Gauss-Markov assumptions cannot hold. The same will be true for ADL P, Q models when P is greater than or equal to 1. ADL 0, Q, yes, the Gauss-Markov can hold. ADL P, Q with P greater than or equal to 1, no, it cannot. However, and fortunately, the thing we lose only is unbiasedness. We can quite often save consistency, so the OLS estimator in general tend to be consistent. We do need to have some conditions, additional conditions on the error term. For example, if we can assume that the error terms are white noise, then the OLS estimator will be consistent, the standard errors will be consistent, and we can estimate an arbitrary ADL model with OLS. We will see later that one of the biggest problems with the ADL P, Q model when P is greater than or equal to 1 is when the error terms are autocorrelated. If they are autocorrelated, then the error terms are not white noise, and in such a case, OLS will actually not be consistent. But we'll come back to that when we talk about autocorrelation.